All right, so the fundamental theorem of algebra just basically says that every polynomial function, and so we're talking degree n, where n is at least 1, has at least one zero in the system of complex numbers. So remember that real numbers are a subset of complex numbers, right? We talked about that back in chapter 2. And your complex numbers, remember, are your numbers of the form a plus bi or a minus bi. And so the real numbers are the special case where b is equal to 0. So really this means that every polynomial function of degree n can be factored into n linear, but not necessarily unique factors. Now these here, these numbers that we're talking about, C1, C2, Cn, whatever, those might be real or complex, okay? We don't know at this stage in the game what they are, but we can get, if it's an nth order polynomial, it can have at least n factors. Now we're not proving this, we're just giving it to y'all. You want a proof on this, go take some higher level math classes. Okay, so we can use this kind of to back things out the other direction. So if I say, hey, find a polynomial function of degree 3 with -1, 0, and 4 as zeros, of course we can write our function, right? We can say, oh, x minus -1, x minus 0, so I'm just going to write x, and I got x minus 4. And that is a polynomial function of degree 3, if we were to multiply it out, that has the 3 zeros that were specified. Now, any constant multiple of this is going to work as well. So if we want to find a sub n, that leading coefficient, we're going to have to use to be given a point on the graph as well. So like this one, we can even sketch it, right? Because we can say, well, there's -1. So there's a root there, there's a root here at 0, and 1, 2, 3, 4. And if we aren't given a point on the graph, we're just going to assume that it has a positive coefficient for the leading coefficient, and we're looking, oops, missed it. We're looking something like this. Close enough. Okay. And of course you can throw that in GeoGebra and graph to verify. Okay, so what if I say, hey, I want a polynomial function of degree 3 with these given numbers as zeros, right? So of course we can go say, okay, great, I got this, x minus the first root times x minus the second root, 1 minus 4i, times x minus the third root, x minus -1. Great. Now, here is usually not going to be a good answer because we really don't like complex answers or complex numbers in our polynomials. Plus. All right, so all I've done here is distribute, right? And so what normally happens is we're going to say, you know, we want the polynomial in factored form, but with all real coefficients, or, you know, that are made up of linear factors and irreducible quadratics, which is what we're going to get if we multiply out these two factors here. Now, this is where that square method can really help you, because this is like 9 multiplications, which is a lot to keep track of. So we're going to write out, right, we've got x minus 1 minus 4i, we've got x minus 1 and plus 4i, and of course we're going to multiply everything out. Minus x plus 1 plus 4ix, no, just 4i, sorry. Let's see, x times 4i, so 4ix. Negative 4i, and 4i times negative 4i, so negative 16i squared, but r squared is -1. There we go. Okay, so here, this is nice because we can see, oh, look, these guys are going to cancel. These guys are going to cancel. The other ones do not cancel, but now we know we got x squared minus 2x plus 17. And now we have our function as a linear function, a linear factor rather, and what we generally call as an irreducible quadratic factor. Okay, so there we go. Let's see, what do we got next? So we have another example, but we're at the 5-minute mark, so let's go ahead and stop for the next video.